Hello everyone! Alright, it is velocity time, it is note-taking time. Let's talk about it. Alright, velocity is a vector measurement. Remember, a vector means it is a measurement that has both direction and a magnitude. How much? Velocity has both of those things. So velocity is an object's speed in a particular direction. So the way we calculate that is to find the displacement and divide that displacement by time. So velocity is equal to those two things divided. So velocities in that case can either be positive because they're moving forward, or they can be negative because they're pushing backwards. But there's a key difference between speed and velocity. I think the easiest way to see that is to look at a really cool race. So let's look at this really quick YouTube clip of the 500-meter dash run by Usain Bolt. He's a pretty fast guy. Let's see what he has. Sorry, I wanted to make the video big really quick. Let's watch it. Turn up the volume so you guys can hear it.
1976 och 1958. Jag tror inte på världsrekordet.
Hittills har ju den här mannen alltid överträffat alla förväntningar, så att ja, varför inte ett världsrekord? Det är perfekta förhållanden.
The 200-meter dash is a sprint that requires tremendous amounts of athleticism. In 2009, here in Berlin, Usain Bolt broke the world record for the 200 meter with a time of 19.19 seconds. How fast was he going? Well, that depends on how you look at it. How fast Usain Bolt was going depends on if you look at his average speed or his average velocity. Speed is given by the distance over time, whereas velocity...
Here's already one key difference between both speed and velocity. Velocity is equal to displacement divided by time, while speed is equal to distance divided by time. Now, that might not seem like a big difference, but we'll see in a moment what big difference those two things can make when we try and compare how fast someone goes in a race.
Is given by the displacement over time. We'll look at each of these separately. First, let's look at his average speed. When considering the same average speed, we consider the entire distance he ran around the track, which is a total of 200 meters. So we get that the average speed is 200 meters over 19.19 seconds. This gives us a total of 10.422 meters per second. Now let's look at velocity. When considering Usain's average velocity, we only consider the distance between his starting and ending position, which is about 115 meters. So we get that the average velocity is 115 meters over 19.19 seconds, which only gives 5.993 meters per second.
Alright.
And how you look at it...
So that was a little hard to see. I was trying to zoom in there. Let's take a look at that, right? Let's take a look at that one more time. I've moved it onto YouTube, so it's a little easier
How
to
you
see.
look at it...
Alright, so if we look at the distance is the total amount he ran, because for distance, we care about every step he took. He took 200 meters here. His distance is 200 meters, so this is for speed, right? And he ran these 200 meters in 19.19 seconds. So when you divide those two numbers, you get 10.422 meters a second. That's Usain Bolt's speed. His displacement is going to be a little different, though. Because remember, displacement cares only about where you start and where you stop. So here's our starting point, and here's our ending point. So the distance is going to be different from displacement. In this case, displacement is 115 meters. Time's still the same. Time doesn't change. Time is still 19.19 seconds. So velocity is displacement, which is this, divided by time. So our velocity is equal to 5.99 meters per second. That's different from our speed. Our speed was 10.4, and our velocity here is 5.9. See, the difference between the two is that speed is concerned with distance, this whole 200 meters, while velocity is more concerned with the displacement, which is this right here, the 115 meters between your start and your end point. That's the big difference between the two. Alright, so velocity is not the only thing we're going to talk about today. Velocity leads to a very important concept called acceleration. Acceleration is a change in velocity over a certain period of time. So if we wanted to measure acceleration, we would subtract final velocity from the initial velocity and divide it by time. Units for acceleration are meters per second squared. And we can also get slower, right? Deacceleration is a thing. If something deaccelerates, it becomes slower, and we will show that as a negative acceleration. All right, so now that I've talked about it, let's look at a sample problem here. Let me move this over, and let me get out my MS Paint. Perfect. All right, so Mr. Engling is late for work, so he increases the velocity of his car from 45 meters a second to 75 meters per second over 6 seconds. What is Mr. Engling's acceleration? So, remember our formula for acceleration. Acceleration is A is equal to VF, which is our final velocity, minus our initial velocity divided by time. Alright, so in this case, Mr. Engling, his final velocity is 75 meters per second. You subtract that from the initial velocity, which is 45 meters a second, and you divide that by time. In this case, it's over 6 seconds, and then you divide that out. Now, if you want, you can use a calculator on the test, but this is pretty simple math. 75 minus 45 is 30 meters per second over 6. And that will give us, oops, hard to see with my face in the way here, is 5 meters per second squared. There is our acceleration. All right, I'm going to clear the board here real fast. And we're going to go and do one more problem. So let me clear this real quick. 1, 2, all right, ta-da! All right, all clean. All right, let's do one more problem. Mr. Engling is revving his engine. His car is not moving. Then the race starts. He accelerates 10 meters per second squared for 13 seconds. What will Mr. Engling's final velocity be after he drives for 13 seconds? So, in this case, if we want to figure out what my final velocity will be, what we need to do is we need to plug in what we know. So we know my acceleration. My acceleration is here. When you see meters per second squared, that's a clue telling you that this is an acceleration value. So we know our acceleration A is 10. That's equal to, well, we don't know final velocity. We need to figure that out. So final velocity minus initial velocity. What was my initial velocity? Well, at the beginning of the race, the car is not moving. Since the car is not moving, in the beginning we're moving 0 meters per second. And this is divided by time. So this is over 13 seconds. All right, now if we simplify things, we have 10 is equal to VF over 13 seconds. Now, we need to simplify some variables here, right? So we need to find VF, so we're going to multiply both sides by 13. That's going to get rid of 13 on one side. And it's going to isolate VF by itself on one side, which will give us VF is equal to 130 meters per second. All right, that's an example of an acceleration problem. It works pretty well. Let's go back to our notes here. There's a few more things we need to talk about before we stop for today. So, let's talk about graphs, and let's talk about graphs in accordance to velocity and acceleration. We can graph both velocity and acceleration, but normally what you do is you graph velocity versus time. Velocity goes on the side, and time goes on the bottom. That's how it normally always works. When you do this, when you graph velocity on the side and time on the bottom, what this does is that it shows you acceleration. Here we have two things accelerating. The pink one is slightly faster, and you can see that because the slope is steeper. It points up a little bit more than this one does. Here, this straight line, we have zero acceleration because the velocity is constant. And here, we have deceleration. Something is slowing down because we have a slope pointing down. Now, finally, when it comes to velocity time graphs, the final thing that it can do that's very helpful for us is that it can tell us the distance something went. If we take the area underneath the line, this is the line, if we take the area underneath this line, a velocity and time graph can tell us the distance of how far something went. So in this case, the area, we would have to take the area of this rectangle and the area of this triangle. And if we found the area of those two things and add them together, we would find the distance that something moved. And that's why these velocity time graphs are pretty useful, because they'll tell us how far something went. All right, so that's it. Those are your notes for the day. After this, you guys are going to get a practice worksheet. The practice worksheet is going to have a combination of acceleration problems and some speed problems and a graph. You guys, good luck on those. If you don't finish those today, we'll work on some of those tomorrow. If you have any questions, feel free to email me, but know I'm going to be in class tomorrow and you can ask me whatever you need, all right? All right, I'll see you all later. You guys have a great rest of the day. Bye.